the life cycle modeling component of the Joe model takes the like original concepts with the stressor response curves, but then it links it into a matrix population model. So the idea is to run simulations with stressor response curves linked to specific vital rates, and then look at the relative differences across scenarios too. So the life cycle model itself was developed, or a majority of the code was developed by Adam Vanderlee and Martin Coops, and then it was readapted by a fellow named Kyle Wilson, who is with Secura now. And then I also kind of readapted it too, and then put it into the Shiny application here. But the life cycle modeling component, or just the assumption behind it, is you have, rather than just kind of like an adult system capacity, we know that like different stressors will be linked to different endpoints, and they might occur at different life stages too. So if there's like specific bottlenecks, and there's like a density dependent bottleneck for say like the recruitment of PAR or something too, and then it gets hit by a whole bunch of stressors after that, you might get really interesting effects in trade-offs too. And so if there's other ways to model that too, running life cycle models in cumulative effect assessments too isn't particularly novel too. It's been done for a long time, but like as Jordan mentioned earlier, a lot of the modeling tends to get really complex really fast, and it becomes like pretty entrenched for a specific case study application. So the idea here was to try to kind of develop a bit more of a generalizable framework and tool that doesn't have like all of the specifics for a given case study, but can still be kind of adapted further. So the kind of inspiration from this came from the original study from Adam Vanderlee and Martin Coops, looking at West Slope cutthroat trout in the Saskatchewan Nelson River too. And so it's just a generalized, under the hood, it's just a basic stage structured matrix population model. And then it's also kind of borrowed heavily from work from a group of individuals down in the States there, from Tim Vici and Mark Sorrell and Jorgensen there, who have been doing a series of really related studies to look at these kind of like stage structured life cycle models mixed with stressor response curves, and then kind of thinking about them in a cumulative effect framework for thinking about risks and priority actions there and so on. So yeah, here's sort of just an example from that Tim paper from Vici et al. 2021, where it's looking at like a series of different scenarios similar to the Joe model, and you can like kind of try to think about different restoration actions or stressors, and then kind of on the y-axis here have some sort of response for capacity of adults or productivity and so on. So where does this kind of link into the stuff we talked about this morning? Is you're looking at this stage structured model, and then you have your stressor response curves, but rather than kind of linking them to system capacity writ large, you're thinking about their effects on survival capacity or fecundity. And this may not be appropriate for all applications, but if you're at the point for your case study where it makes sense to do so, to try to find specific linkages for a given stressor to a different life stage here. So in here, we're showing something like, you could have something like stream temperature affects their survival of fry rearing too. So you would link that to fry to PAR survivorship as sort of a rate modifier there. Kind of designing these studies, again, this is borrowing from the work from Tim Vici and the others there too, but it's like setting up the life cycle model is a bit more involved than the Joe model. So you have to kind of really put everything down on paper and kind of think about external drivers at the top level of things that you're sort of interested in. And then at the next level, thinking about how, like, what kind of elements and components of the life stage does it link into? Like, does this change fry habitat or spawning habitat and so on? And then from there, kind of on the third level down, is thinking about which vital rates do they modify? Like, is this something that changes capacity, or is it something that changes survivorship and so on too? And then from there, you're kind of running the population model to look at changes to capacity and productivity too. So yeah, again, kind of just thinking about the stuff again that Lauren and Jordan worked through too is really kind of thinking about the stressor response curves from like the more proximate to ultimate, and then really framing them in components of the life cycle here. The life cycle modeling framework too, like the design of this is to be as generalizable and broadly useful as possible too, but it might, like there are lots of other applications out there that are really tailored to a specific example, like thinking about hybridization and gene flow or something like that too, that this population model doesn't consider too. But the idea is to kind of think about the stressors and run different what if scenarios, but then link components up to a population model. Yeah, and just kind of the intended use case when you're thinking about these population models is you're all running simulations too. So they're really good at looking at the relative direction and magnitude of the effect of different scenarios, but they're less ideal for trying to like come up with specific carrying capacity estimates or like hindcasting what happened on a given year to, or other kind of more specific components of inference there. So yeah, just as a quick population biology refresher too, is we usually, the idea in the population model is you're breaking down your population just into discrete endpoints. So if you're thinking about salmon, maybe that's like eggs, fry, par, and so on. And then kind of thinking about these life stage breakpoints in annual time steps too. And so it's a bit like you just draw a life cycle diagram, and then from there you try to estimate all the different parameters in red here. So you try to think about your egg survivorship, your fry survivorship, and then the survivorship in years and so on too. In almost all cases for any trout or salmonids too, there's a large library of different resources that people will go to fill in these values too. Yeah, and then there's a series of input values that then create a transition matrix. The tool does this itself, but this is how the population's projected forward is a population model transition matrix. So it's the probability of moving from one stage to the next. In the model itself, though, is like, what do you actually need to provide? Is the only thing that's new is a life cycle file here. And so the life cycle file is specific to each kind of species or population there too. So you might have like a life cycle file for Athabasca rainbow trout. There might be a life cycle file for coho in the Nicola too, and they might be subtly different, and others could be the same. Depending on how specific you want to be, you can borrow vital rates and parameters from other study systems, or you can go on to create your own from scratch. There's a series of standardized inputs for each of these two, which the guidance document kind of walks through developing one of these life cycle files. I'm not going to go through all of them, but they're kind of fairly standard inputs like egg survivorship, fry survivorship, years in this stage, and so on too. There's also a component of density dependence in the model. So these are some slides showing some work that Wilson did there too. So within, sorry, I'll come back to density dependence in a moment too. But within the stressor response relation, stressor response file, then we have the option to link specific stressors to specific components of the life cycle here. So just where I have my mouse here on the stressor response file, if you leave these blank, that's fine. It'll just run the Joe model. But if you want to specify these, you can think about it as a given stressor, link it to a specific life stage, and then link it to either it's going to change survival, it's going to change capacity, or it's going to change fecundity if that life stage is relevant there. And so the way that it works is it's going to just make a relative change. So like if you think that your egg survival is going to be 30%. So like under default conditions or base case status quo conditions, an average egg has a 30% chance of surviving. And like, let's say a given stressor knocks it down by 50% too. It'll just change when the model runs, it'll change that value from 30% to 15% too. Yeah, so these are the two new columns in the stressor response workbook here, which you can leave them blank if you're just working with the Joe model, but if you want to run a life cycle model, then you can specify these stressor response linkages. Then we think, so yeah, the previous example is kind of thinking about density independent runs too. And then the next component is thinking about density dependence. So in the life cycle model, density dependence is modeled with Bedford and Holt constraints on different life stages and different locations. So you can optionally specify these for any given life stage that you think has a density dependent bottleneck. So if I thought fry to par had a bottleneck for a specific system, then I could specify a carrying capacity for that life stage for that location. So what that looks like in the tool is there's actually one other input that you can specify for these location and habitats density dependent constraints. So this is similar to the stressor magnitude file, where we have all our different watersheds and watershed IDs. And then across each of the columns here is our carrying capacity for each of the life stage values here. So in this case, like if my life stage 1 was par, and my carrying capacity was 1200 par there, then I'd put that in that cell. So that specific watershed subbasin or location number 1 would restrict the number of par via a Bedford and Holt density dependent curve. You can also include these CV values too to show that the carrying capacity or just the baseline habitat availability will change by some coefficient of variation there or standard deviation there. The guidance document goes into a bit more detail about how exactly to kind of make these and other things to think about. But the idea is it's just like you can choose which life stages you think are going to have density dependent caps on them. And then wherever you specify one of these, the model will run with density dependence. There's another option too. So you can, that's one way to do density dependence. Another option is to use compensation ratios too. So this is like a little bit more down like the rabbit hole of population biology too, but you can have just a starting carrying capacity of adults. So like if you knew that there were going to be like 500 spawners in your system and you knew the ratio of smolts and the ratio of other life stages, you could use these compensation ratios that they're a little bit hypothetical too, but you look at like a stable stage distribution and then it lets you run the model with density dependence without actually specifying carrying capacities and habitat availability. I could go elaborate on this a bit further if anyone really wants to, but the guidance document dives into a bit more detail here. But this is one area where it does kind of get into the weeds of population biology, but this is one option to implement. You don't have to use these two. Here's an example of compensation ratios. So it's kind of like the gas pedal and the brake on baseline survivorship for a given life stage there. So yeah, this is kind of going on with another example that Dr. Kyle Wilson put together for Athabasca rainbow trout too. And one of the things we were looking at here is yeah, we kind of have the assumption that like the more complex and nuanced model will provide like a better result. there too. And this example, these were just like some draft results here, but we're looking at kind of the cumulative system capacity on the x-axis from the Joe model, and then on the y-axis, relative change in carrying capacity too. And just, I thought this was an interesting example to show that, yeah, there are differences between the Joe model and the life cycle model, but just because you can, it doesn't, obviously this is going to change for every single case study you look at too, but just another thing to think about, like in some cases they will be different, in others they will be the same, but it's not necessarily like always better or more nuanced there.
So just to comment on that, the black line is the one-to-one fit where they're predicting the same thing. And the Joe model and the population model are pretty close for the most
part. Yeah, again, another example too. So you can set these up with different life stages and different levels of complexity there. So this was just an example for Chinook salmon in the Nicola River too. And again, this was kind of thinking about different stressors on the x-axis and then their relative effect on the y-axis under a series of stochastic simulations. So this was kind of thinking about which stressors have the strongest effect on the population and what's kind of the shape of the dose response curve with kind of the relative abundance of adults on the y-axis too, and kind of looking at like scatter and sensitivity there. And so the spring flow was pretty insensitive there, but it's like habitat quality and other stressors had potentially a huge effect too. So yeah, I'll just kind of break here and then I'll run into some life cycle or some demos using the life cycle model example data sets. I'm just going to use the Athabasca rainbow trout example. And I'll restart the application. Yeah, so this is the sample input file here for the life cycle profile. So this is all the information that the life cycle model will be based on. The name and the values column, these are fixed too, but the parameter nicknames is you can put whatever you want in there. The idea is that each of these different life cycle profiles will represent a different species or population of interest there. So if I load a different one up, so I could load like an example, like if that was Athabasca rainbow trout, maybe I could try an example for coho and it might look a little bit different. So in this one, yeah, and then in this example for coho, I only have 3 unique stage classes, whereas in the Athabasca, I have 4. And all the different parameters are a little bit different too, to reflect the population dynamics of coho versus rainbow trout there. But that's what the life cycle models look like too. Coming up with these values too, it's best if you can try to find reference life cycle models in the literature too, and if you find a good case study, they have all the same sort of values in here, but depending on your specific study system and how different it is too, it might be worthwhile even doing a feasibility check up front too, just to think about whether you can reasonably approximate all of these, or if it's like a data poor species at risk, is there something else or like 2 other species that you could use as a proxy or their populations too. So kind of that level of planning and representation could be important there. Anyhow, so when you've got that all set up, you can upload it into the tool here. So Yeah, so I'll just change one of these. So make it my eggs per spawners 1100. And then when I'm all happy with that, I could upload that into the tool. And then when I go back to this population model input page, it looks, oh, sorry, I'm just going to share screen differently so that black bar is gone. Yeah, so this is the life cycle model, population model calibration page. It looks a little bit intimidating here in the beginning, but all these inputs here are the same inputs that were in that CSV file. They're just organized here with labels in wording here. The other components that we see here on the screen are yeah, so there's all the inputs we see from the CSV file. And then to the side panel, there's different elements for looking at summary statistics, and then an option to run different population projection time series forward in time. So here we kind of see from our previous example, there's sort of a standard workflow we'd follow here as we kind of set and update the inputs. So you can go in here into the, oh, sorry guys, the Zoom is just a bit tricky to. Yeah, so I can go in here and then I can change some of these inputs. So if I thought the survival of eggs should be a bit different too, I can kind of see in real time how there's just some of these different summary statistics. So thinking about the productivity or the lambda value, then I can go on and change assumptions about the reproduction, density dependence, and so on. This whole panel here is a bit more of an educational tool too, just kind of thinking about components of population ecology and population modeling. So there's some other options here to kind of show the transition matrix and some of these other stable stage distributions and so on. But then what else is neat here is I can kind of run some hypothetical population projections in just this little sandbox here. So if I click the number of years and the number of replicates, I can just kind of run a sample time series forward, and it'll project my population forward in time. If I'm just thinking about different stressor response relationships and like how that might go about to change components of the population, I can. So if I'm looking at temperature par, like let's say it's going to be 16 degrees, we'll just use that as an example, but I can run the population by changing some elements here. So I can change components of the life cycle, or I can add different stressors here. So I can make the temperature specific range, and then I can rerun my simulations here. And then, oops. Yeah, so it shows the current run and the previous run. So when I made those changes, for whatever reason, it started at a higher abundance, but then it quickly declined too. So I made the adults, I changed the fecundity, I increased it, but I also made the stream way hotter there. And so in this current run, it's reduced by half from the original. So kind of from there, we can kind of see an example how you can start to think about how you might run scenarios with a life cycle model, is looking at kind of the relative difference between a base case and then a scenario case there. And so that's kind of in this whole component here is it's sort of just like exploration and calibration here, but I can go back to the main map window here. And see. yeah, all these temperature values are fake. I just randomly put them in for a demo too, so it's not for some reason hotter in the center. But I'll click on a few example watersheds. So if I want to run the population model across these three, I can run, oh, sorry, I clicked on that little tab that said population model there too. Then I can run the population model on specific watersheds now. And so in this case, it runs forward and it draws these using all the assumptions in the population model. It just runs these projections forward. So you can kind of look at relative differences across individual watersheds or life stages too. Here's sort of that from those other examples too. It's showing the relative abundance of different life stages for different watersheds. And these are just like some little exploratory tools that are embedded into the app that you can kind of run. And so you can see one of these watersheds, I guess it was the one that was too hot there, had the lowest abundance, and then the other two are in the middle, and then includes one where there's no stressors, just as a base case for a reference point too. This final plot here is just showing, since each of the stressors are stochastically resampled, it just shows for each of the runs, for each of the watersheds, where the values landed there too. So there's like these ones were randomly sampled. There's like our red watershed, which is, or that 101 is down here, and then the other one's up at the top end there. Yeah, and so that's an example of what running the population model in the tool itself. There's another example here. I'll just show. In a lot of cases, though, running the population model. Screen share. Yeah, running the population model in the Shiny application might not give you quite enough flexibility that you need for your specific case study. So again, there's a series of these tutorials for within the R package here, which show some examples of running the population model just in R too, using the same code. So it's the same kind of setup as before, as it inputs the species profiles. There's ways to kind of look at some components of it, and then you can run the populations forward in time. You can add in different stressors and so on. There's a few different tutorials here. So this is an example of doing a batch run. Again, it's, let's try to find the right part here. Yeah, it's the same sort of thing, but you're just using the R package now. We're loading the stressor response file. We're loading the stressor magnitude file and the life cycle file. And then we run the population model forward time. And then in this case, just do a quick visualization plot. And so there's this baseline run in red here. And then there's a run with the cumulative effect stressors. And in this specific example, the population gets reduced by 25%-ish there relative to the baseline too. But yeah, and the R package is useful just because depending on exactly how you want your inputs to be set up and what you want to do with outputs, or if you want to include loops, it's useful to have that as a component in there as well. Just some kind of closing thoughts on the population model here. Yeah, and so for creating your own species profile, the best way to start is by drawing out a life cycle diagram, kind of planning when the events occur. So this is an example for coho salmon, like tying in components of the life cycle into maybe into a bit of a calendar thinking, like drawing arrows about where the stressors interact with them and when too. And this can help kind of like illustrating it in a diagram is really useful for deciding exactly how it should be set up too. Then you can kind of take something like this and convert it into one of those life cycle input files. And then finally, the life cycle model, tying it all together, is bringing in the life cycle profile, bringing in the stressor response relationships, thinking about specific habitat availability if there's a density dependent bottleneck somewhere, and then tying those into stressor magnitude files, and then running those together into scenarios too. And that's sort of like the common workflow in the life cycle model. And yeah, with that, like I'll see if there's any other questions here, and then I think we'll take a break for 15 minutes, and then we can go over some of the other components of the tool there.